So I'm going to begin with some acknowledgements. First of all, I'm the land acknowledgement. I'm in Ottawa, so I'm on Anishinaabe territory, unceded Anishinaabe territory, and yeah, I think there's some. Anyways. And I'd like to acknowledge many thanks to the Lancy as well. I've done all of the calculations on their computer. To the Geography of Philosophy project as well. I'm doing my postdoc there with Edouard Machery. And to the SSRHRC, which is funding my postdoc. So I decided to, I got the invitation for the workshop, and I wasn't too sure what I would present, but I was, as part of the GPP, I was working on contextualize word embeddings. So I thought I'd just, try a few things, see if it could help the problem of classification. And I put the title "Language Model Revolution" because that's a lot how the computer scientists think about it. But I was kind of skeptical going into it, and you'll see I had some interesting findings with that. So, what are language models? Well, there's another definition of what is a language model, which is just like a sort of supervised algorithm. But what we mean nowadays when we talk about language model, usually we think about things like BERT or GPT-2 or 3. And these are a specific type of machine learning algorithm. These are neural networks. They're extremely deep. So BERT in particular, I think it's 12 levels, and they use the transformer architecture, which I'm not going to explain here. Besides, I don't really understand it, but it's an evolution of the neural networks. And basically, how it works is that you train it on a sort of toy tasks. So very often it's things that don't require too much annotations, but is still kind of supervised like a language model. And you train it on very large amount of data. And then you can use them on downstream tasks. So typically how you do that is you're going to just add a layer on top of the neural network, and then you fine tune it, which is to say like you train it on your task for a little more time, and then that gives you some results. So for instance here, I got that from somebody else, obviously. You're trying to say whether an email is spam or not. Well, you would add this layer, the classifier here. I don't know if you see my mouse. And you train it for a while. And given that it already has all the information in the language model, you would expect to have much better results. And so BERT in particular is trained on two tasks. One is mask language model, which is you take out a few words and ask the machine learning algorithm to predict the missing words, and the other one is predicting the next sentence. So it kind of has this nice thing of having both close context and larger, what they call discourse context, that is learned by the algorithm. So the thing is, with neural networks in general, there's always this sense that we don't really know what the algorithms are doing. But when you have like 12 layers, it becomes even more the case. And therefore, there has been this thing where a few papers have been coming out. People have been looking at how sorry, what these models are good at. And BERT in particular has been the subject of many of those. In some studies, they've shown it can infer semantic roles, semantic relations. It can also infer, it's really good with part of speech tagging. It's pretty good with syntactic roles too, detecting subject predicate relations, these kind of things. There's some word knowledge in it. Interesting thing, it's really, really good with multilingual data. But in particular, it's these are what they use for the best machine translation things nowadays. Although, like, you know, there's various things that we can do with multilingual data, so it's still to be studied. It also struggles with some things. So like many machine learning things, it's really bad with negations. It struggles with numbers, which it's not good with reasoning tasks, and it's not good with malform input. And maybe interestingly here, because I'm going to come back with it, it's not good with like people who've been using word embeddings know that you can see whether two words are kind of synonyms or functionally close, what I call maybe in linguistic literature, they will call that like paradigmatic relations. Cosine similarities will between word embeddings will help you with that. So these language models sometimes are classified as contextualized word embeddings because they provide vector relations for words in context. But cosine similarity, in principle, doesn't work. But you'll see that there's there's difficulties with that. So in theory, I'm going to present two tasks first. So one is classification, that's like supervised kind. The other one is topic model or clustering. So that's kind of the unsupervised equivalent to that. So, you know, I have data 10,000 abstract from field papers. I took the 80 most common classifications, and then I just used the really simple transformers Python package, and I compared it with the classical multi-label classification algorithms that you find in scikit-learn. And well, these metrics, the label ranked average precision and the F1 score. So the label ranking average precision is the standard one that they use in simple transformer, and it's how the score rankings compare with the ground truth. Whereas F1 score is really like prediction and ground truth. It doesn't look at the score, and it's a harmonic mean of precision and recall. So a lot of people would be familiar with that. There's some literature that has done similar stuff, and I'm really just showing you to tell you that I was expecting this task to work really well, because BERT has been hailed as giving among the, at least when it came out, the best performance on that. And here the AAPD is actually academic papers. There's 56 labels, 40,000 documents. So it's kind of really close to the kind of corpus I was giving to my language models. And you know, it performs state of the art in this compared to not only, you know, SVM, but also like convolutional neural net, LSTM, etc., etc. So that seemed to be working really well. But when I tried it, I tried various language models, the ones that wouldn't cause out of memory errors. And that doesn't seem to work really well. As you see, like the F1 is abysmal, which, you know, there's 80 categories, but still, and the MLP classifier is multi-layer perceptron, and it compares very favorably to all these models. I can't really tell you exactly what happened there. I can tell you that I tried over and over with different hyperparameterization. There's not much difference between what I think I have done and what Dogbert has done. I spent way too much time on this, and somehow it doesn't seem to be working too well, and I'm not exactly sure why. But I do know that if I change the sample, the results change a lot. Like I worked on another sample, and the results were much closer to what the scikit-learn's algorithms were getting, but still not very good. So that was a bit of a disappointment. I was expecting topic modeling to go a lot worse. And you know, it's because BERT is not really made for that. Also because, well, the maker of BERT, his name is Devlin, he stated that, well, the BERT model is not supposed to give really good distance metrics. And the reason he gives is that the vectors that you get, you don't know how every feature should be weighted. So in theory, it's not supposed to work so well, but you know, you can always try. So let's go for that. One option would be to make, so there's, you know, the whole probabilistic model paradigm. Some of them have been made to work on word embeddings. This is my favorite one, the LCTM, latent concept topic model. For me, it's worked really well. I used it in my PhD thesis. Unfortunately, I tried to apply it, and I managed to, but it's like it takes about a day and a half to learn a model, and unfortunately the model didn't save the right way, and that was like last night, so I can't show you results on that. But fortunately, there's easier methods, in particular k-means. The nice thing about BERT is that since you have contextualized representation for each word, you can take those representations and apply a k-means. Now, you know, k-mean is a fast algorithm. There's been also some developments in how to calculate the distance in a large matrix. So you can have like a really fast k-means, and then from that you can infer topic distributions from the number of words in a document that belongs to this or that topic. So again, the same abstracts. I did add another 10,000 abstract for a certain kind of evaluation. The vectors were trained using the Albert Bayes model. The reason is it's a light model. It seems to be giving good results, and also it's fast. So, and like that's, you know, that kind of start to count. I tried regular LDA without using vectors, but using the same tokenization that Albert gives me, and then k-means with 80 topics for the same reason as before. And then the evaluations, I picked those four from a paper. The first one is the classical perplexity. Like basically, it's calculated from the probability of the words given the topic model. The other ones are more about words. So internal, external coherence is like you take the top words in every topic, you try to see like, do these words come together, and you evaluate that on your corpus and on another corpus. Exclusivity is like, how exclusive is a word to a given topic. If you want the words that that are associated to a topic to be more exclusive to the topic, ideally. Word entropy is a bit, it's actually meant to be a kind of proxy of how specific is a topic. And so that's more something that tells you about like the kind of topic that you have and the quality of the topic model. But in any case, so the results you have, like, first of all, perplexity is much higher with LDA. So that you have a big gain here. And when it comes to internal coherence, you can see k-means is higher. Same thing with external coherence. When you apply it with an external corpus, k-means is still higher. Exclusivity, the words are more exclusive, so you would expect them to be more telling of the kind of topics that you have. And it also seems to be that the topic seems to be slightly more specific. So that's interesting. For comparison, so this is another paper from Laura Thompson and David Mimno. So they actually got results that were really close to with a similar method. They got results that were really close to the LDA. So I was not expecting to have topic models work so well with that specific corpus. Lastly, I tried stuff like trying to see maybe something that's more in tune with maybe what BERT can actually bring us. So it's a bit like the kind of things that Joe was presenting. It's kind of interesting that now that you have representations of words that are attuned to their single context, what you can do is try to see like, well, maybe like, how does these words evolve through time? How are they used? So of course, I didn't have like as much time and data as Joe had, but you can still see that in many words, you can see interesting trends. So, for instance, in the wise thing, you have a rise of the religious topic. That's actually, so this topic is a bit like also like maybe not just Western but also Eastern religion. So I wonder if that's the reason why, as you know, we're looking a little bit more outside of Western philosophy, that becomes interesting. There's like an interesting peak here with the handicap concept. And you see that this peak is really driven by the social institutions cluster. That's, well, in 1989, I think or 1988, you had the Americans with Disability Act. So I think that's definitely what pushed for more publications on the thing in the 5 years, well, in the few years that followed. And for something more recent, well, you know, you have a big spike with algorithm, and it's largely driven with the authority subset, which, you know, I think reflects our interest in the social things going on there. So maybe, you know, coming back to our two tasks. So why is classification so bad? I honestly don't know. Size, label, genre are similar to DocBERT. I tried various hyperparameters. I have to admit, like, that in yeah, in some cases, like there might be a lot of variation over the random initialization parameter. You have a lot of difference between some models and others, but still, it's a bit of a mystery for me. On the other hand, why are our topic models so good? Again, I'm not so sure, but you know, topic models that use word embeddings were already pretty successful. So maybe there's something about that, and you know, you have a lot more information when you include information from exterior corpus. And the thing is, maybe, you know, topic coherence might encompass a variety of linguistic relationships. And I think that that's also a point that comes from the sort of Bertology. Whereas I was really, I used to consider word embeddings as really, you know, encompassing paradigmatic relationships, whereas, you know, coherence and topic models were much more showing syntagmatic relations. I think it's more complicated with BERT. So maybe, you know, it just touches about something that works well with philosophy text, and we'll have to find out what it is. So some takeaways, well, you know, performances vary a lot, somewhat unpredictably. So, you know, it sort of tells us that maybe we need, when it comes to a tool like BERT, we have to try it, evaluate it, maybe not dwell on it too much, but certainly try it and certainly evaluate it, which is not something that computer scientists do all the time, I'm sorry to say. We have to take into account that proficiency might go beyond the intended purpose. And I'm not the only one to find that out. So it pays to be creative, well, sometimes at least. And you have to think that it requires important computational resources. So maybe for fill papers, if you're able to create an index with word representations for all the words in abstract, for instance, it might be worthwhile, especially since, you know, things like similarity search, now we have efficient methods. On the other hand, the training of those representations takes a lot of time, takes a lot of computational resources. I'm lucky enough to have like good hardware, but like that's not necessarily the case of everyone. I do think it opens up new horizons. One thing I haven't tried as much as I wanted was cross-lingual work, but that's partly because there's not a lot of things that are not in English in field papers. And well, I don't really know from the Bertology what works well and what doesn't. And I think that's going to have to be an empirical work. And there is something called aligned word embeddings, where you take word embedding models and you try to align them between two languages. In some cases, it might be better too. I think it's interesting to look at the variation across word contexts for the purpose that Joe talked about. I wonder if there's not a solution to the problem I was talking about, to where, you know, you could facilitate the study of a concept even when it changes its token, because you would have like similar word representations. And finally, I think there's potential for new linguistic observables, but maybe that's going to be more interesting in like 10 years from now, when computer scientists will have done more study on this thing, and we'll have a clearer idea of what kind of linguistic and conceptual relationships are in those models. So That's it.